So I'm going to talk a little bit about essentially what bonding is in electrons as waves, right? So when we draw electrons like this as orbitals, we're not thinking about electrons, right? Sometimes you think about electrons, and something like this is ketone. You think of these electrons as particles. Electrons don't always act as particles. They also act as waves. They have wave-particle duality. The biggest thing with that is, how do we think about electrons as waves? When we draw them as orbitals, we're thinking about electrons as waves. We're thinking about them as waves. And so this shading represents something to do with waves. So the shading, sometimes people think, well, if it's shaded, that's where the electron's at, and then they're not here. That's not what it means. And it even gets more confusing. Sometimes people will put, a plus and a minus. That also has nothing to do with charge. It has to do with phasing. And if we take it back one step further, let's think about actual waves, like waves in the ocean, right? So let's literally think about waves. Now, do waves only exist above the water, or do they exist below the water too? Below and above. That's right. So if this, I'll use the blue. So that's the water line, actually, right? So we would think that some of the part of the wave exists above the water and some of it exists below the water. Right? The example I used in class was, if you walked to the end of a dock and dropped a rock in the water, you're going to make waves, right? If you take one step to the left and drop another rock, what's going to happen with the waves you just made with the old waves? They're going to interact with each other somehow, right? Some waves are going to get bigger. Some are going to be just no waves. That's exactly what happens with electrons and these waves, right? Think of this as waves. If the waves are interacting in a constructive sense, right, like they are here, see how they're in the same phase? We call this a bonding interaction. So if I drew another wave here, right? So if I added these two waves together, the waves are going to get bigger, both above the surface and below the surface, right? If I added these two things together, I'm going to make a bigger wave. That's like saying I'm making a bond. Right? They're going to orbitals, the electrons are going to interact in a constructive manner. They're going to form a bond. Now the problem is, right? Not the problem, but for every action, there's an equal and opposite reaction, right? There's matter and antimatter. There's the dark side, and then there's the non-dark side, right? Same way with bonds. So if this is a bonding interaction, two waves coming together in a positive sense, right? Well, not positive that way, but we also would make a antibond. And so what antibond looks like, and you've probably seen this before too, the phases don't match up. Right? This is forming an antibonding orbital. So we call this a pi star, you've probably seen. And this is a destructive interaction. This is when two waves come together and don't make each other bigger. It's actually a destructive interaction. It's an antibond. Whereas this, right, was a pi bond, we call it. So electrons as waves are interacting either in a constructive or destructive sense. When we draw orbitals, right, when we draw p orbitals or s orbitals or sp3 or sp2, we're actually saying this is where the electron is. The electron is this orbital, is this shape. This is where it is, this is where it exists. If they interact in the right way or the right phases, they'll form a bond. If they don't, they'll form an antibond. Now the hard part is, so some part in the textbook, they use different colors, right? So if one part of if this was blue and this was red, you want the blue and blue to match up and the red and red to match up, right? So it's just another way to show this, shading or different colors. Yes, so there are such things. This is a pi star antibond and this is a pi bond, but of course there are sigma bonds, which also means there must be sigma antibonds, sigma stars. If you look at the end of I'll show that part there's a part where we talk about this. So a sigma bond, right? I'm gonna draw a sigma bond, maybe that we're familiar with, hopefully, maybe a little bit. Let's say I have an sp3 orbital coming together with another sp3 orbital, right? And they're forming a sigma bond. Awesome, right? Let's say these are two H's. Or no, it can't be H's. They'll have to be carbons. can't be H's because H's only have how many electrons? So they only have s orbitals, right? Very good. So I'm going to call this let's say this is just a carbon and this is a carbon, right? Awesome. Who owns the electrons more here, carbon or carbon?
They're the same.
They're the same, right? Now what if I made this a bromine? Would the electrons be shared the same?
No.
No. So maybe that's going to come into play tomorrow.
Oh.
So that's where the sigma bond is at. That's where the electrons are at, right? The electrons are here in the middle being shared. Where are electrons not at? Where's sigma star?
With the ends or something?
At the, like
not in the-
literally just the opposite looking type thing. Right, so the red here is sigma star. So these are areas, right? I'm telling you this is where the electrons are at in the bond. The sigma star is telling you where electrons are not at. Now
Wait,
that becomes
where does it
important.
Start exactly. They're two different.
So it's like a space, right? They may act like most of sigma star is out here behind
Okay.
it,
Wait, can you, so sigma star is where electrons are not at?
right? Because it's an anti-bonding. If you guys learned this when you learned about bond order, you remember putting electrons in an anti-bonding orbital, a star orbital. What happened to the bond order? Did it increase or decrease when you put electrons? What do you think is going to happen if I put electrons in an anti-bonding orbital? What's going to happen to the bond?
So it will break.
It'll break. So here's the deal, right? This is why it's going to become really important. Where anti-bonding orbitals are at is going to be really important because that's how you break bonds. And what are we going to do?
Right.
Make and break bonds.
Oh, duh. Interesting.
So if I took a look at this is also where electrons are not at. Just kind of opposite. Sometimes you'll see it kind of stick out a little bit one way or the other. Sometimes they'll draw it like this for pi star. They'll draw it kind of wing it out a little bit.
So the electrons aren't in the shaded part.
No, the electrons aren't in either of these parts.
Alright.
Shading has nothing to do with where electrons are at. Shading never has anything to do with where electrons are at.
So where are the electrons
Nothing.
in that?
They're not here. And there are here between these two.
Oh.
Yeah, it's like a, okay.
Right? So pi bond, remember,
They're forming like a bubble.
they're sharing electrons in this space.
So like where your
And the electrons are not at on the other side over here. I kind of pointed away.
So
Let me just-
that would be,
Yeah, let me just superimpose them, right? So it looks like this.
yeah.
I'm going to emphasize it even more. Like sometimes in the book shows it's like really like them like spreading it across. Right, they're sharing that electrons right there. Right, so that's how they're superimposed. Right, here where electrons are at in the pi bond. Here out here is where they're not, and both it doesn't matter where the shading is.